Thank you.
Much. Thanks again for the invitation to come and talk. Um, I guess my background is more computer vision, and I've spent the last few years thinking about perception from the perspective of self-driving vehicles. I was involved with a startup associated with CMU, and I think it's kind of changed the way I think about vision and machine learning and AI. So I wanted to kind of relay some experiences of what I think the sort of open challenges are. And one way to think about this is clearly there's this incredible excitement in the air about machine learning and AI and generative AI. I've heard people describe this as we sort of are having a dot-com moment. But with all of the incredible sort of success stories, it feels like self-driving, sort of robotics in particular, self-driving, hasn't taken advantage of that yet. And so I'll give some, I guess one of the take-home messages from this talk will be, okay, what do I think at least the open problems are? And one way to kind of phrase the conversation is, in the world of self-driving vehicles, it's kind of interesting for many reasons. One, because this involves such a safety-critical application, all the failures that you probably read in the newspapers actually have a lot of oversight. So every notable failure, there's a National Transportation Safety Board analysis. You can go online and find a huge document that talks about all the errors. In particular, what I'm looking at here is an error associated with a probably well-known crash that was a fatality. There was someone else who was walking a bicycle across a lane, across the street, and the self-driving vehicle crashed and killed that pedestrian. And so the safety report describes a whole bunch of failures, including failures of policy. Why was the safety driver not trained effectively? So maybe there should be other policies for safe operation. But what the report also talks about is actually technical failures from a computer vision perspective. So at least I've never seen this. I've never seen sort of vision talked about in this way. And so what this report shows is essentially what the vision system thought the self-driving car was looking at up until the point of impact. So this is t minus 5 seconds to t minus 1 second. So what happened was essentially the vision system kept flickering in terms of its interpretation of what this person walking across the road was interpreted as. Maybe I'll just sort of read this. The automatic driving system changed the pedestrian's classification several times, alternating between vehicle, bicycle, and other. Because the system never classified the pedestrian as such, the system design excluded tracking history for non-persisting objects, those with changed classifications, and was unable to correctly predict the pedestrian's path. So essentially, I think of this as, from my time in this space, the actual open challenge in self-driving. In my perspective also, I think all embodied perception. And that is, it's actually very hard to come up with a stable interpretation of a dynamic world. If the world was static, I think this is much more easier. That's actually a classic problem in computer vision. Sometimes it's called structure for motion or simultaneous localization and mapping. But when the world is changing, it's actually a moving target, and it's really hard to sort of figure things out. And so what I mean by that is, because the world is changing, imagine you see a flicker in your observation. So a second ago you didn't see anything, but now you see a child appear from behind an occluded bus. And so that very first frame, when you see something that didn't exist before, you have to ask yourself, is this noise in my observation, or is this an actual change of the world? And it's really hard to make that decision or that inference reliably. And although this accident happened back in 2008, you can regularly find examples of Teslas. People put up their such results all the time of inferences that also result in sort of flickering. So here's a case of a horse-drawn carriage where the system doesn't know if it's a bus or a person walking. So this still seems to be a challenge of reliably building a stable interpretation of a world that's always changing. And so the kind of, I guess, approach that I'd like to advocate for is essentially the same progress and innovation that we've seen for foundational models for language, where you can learn at scale by learning models from huge collections of text. But instead, what I would like to do is try to apply those kind of scalable learning algorithms to visual sensor measurements. And what I'm showing on the right-hand side is visualizations of lidar sequences. And so right now, self-driving vehicles are collecting this at scale. But what I'd like to do is sort of build models that can extract the structure of this 3D world. And sometimes I'll use the term 4D because it's actually a three-dimensional world that's changing over time. Let me just see the next slide here. OK, here. One example of this, so I'll show lots of models that try to analyze streams of visual sensor data. And so sometimes it'll be LiDAR, sometimes it'll be RGB, where what I'll do maybe is different than, what I'll advocate for is maybe different than the traditional approach, is that I want to try to make 3D structure, in particular 3D dynamic structure, a first-class citizen. So you folks might have seen something from OpenAI, Sora, which is also trying to build video models and extract structure in a foundational scale. But in that model, 3D structure is emergent. You kind of train it on sort of 2D pixel level tasks, and you hope that 3D structure emerges from learning at scale. And instead, I'm going to talk about models where we build in that 3D structure from a first-class citizen. And at the end, I'm happy to answer questions about the benefits of the approach I'm advocating versus what these other alternatives. And so, by the way, I should mention, if at any point folks have questions or comments, feel free to interrupt me. I'm happy to have this be more of a discussion than a lecture. Okay. So the kinds of, here's a preview of the models that I'll show here. So the input of all of this is just a video sequence, and the output is actually a dynamic reconstruction of a changing world. And from a vision perspective, you might have seen results like this before. But one thing that is different is that usually when you see kind of these kinds of 3D inferences, it's because you have some large 3D data set as a back end. So you can learn from large repositories of 3D scans of people, the shapes of people, sort of body shapes and 3D geometries that you typically see. But what I'm showing here is something that's actually never seen any 3D data before. It's just analyzing the video, and it's trying to explain the pixel movement and what's happening in the video. And it turns out that the best way of explaining it is by inferring a dynamic 3D structure. And because this thing hasn't been trained on 3D models, it doesn't really care if you show a video of a person or a penguin or a dog or a cat. It'll work equally well because it's never, it doesn't require thousands of scans of penguins or thousands of scans of dogs or cats. Okay, let's see here. And let me actually, so skip to this. So the kind of view that I'm advocating is that I'll talk about approaches that, given video sequences, try to infer the structure geometrically of what's there and how it's changing over time. And the hope is that if we do this at scale on lots and lots of videos, because this is not requiring 3D data, we can instead use these 4D structures that we've built from videos as targets for learning self-supervised algorithms. So rather than traditional approaches that, let's say, try to predict pixels, maxed out pixels from other pixels, instead what I'm arguing is let's just try to fit these 4D models and then now distill them into feed-forward models that try to predict these 4D structures just from single images or collection of images. So one thing that I'll show is that the kinds of models on the left-hand side that I'll advocate are pretty expensive and require lots of optimization, so they can never really be run in a car. But the hope is we can do this at scale, learn about the structure of the 4D world, and then distill that into a very fast feed-forward model that could be run on a robot. Okay, so now I want to sort of rely on intuition. Okay, if it's really hard, if it's really this difficult to build dynamic models of a changing world, how let's kind of do a little bit of introspection and ask, how do we do it? And in fact, I actually like asking this question at a more simple level. So how does my dog navigate the world? How does it understand how the world is changing and how it can safely move? Or for that matter, how does a fly navigate a dynamic world? And there exists lots of biological evidence to suggest that motion estimation is really helpful. And one thing I wanted to sort of throw out there is I think there's been this kind of quiet revolution in sort of AI-based motion estimation. And that is, this is one place where it seems like traditionally it's really hard to build motion estimators because you have to assemble a large amount of training data where you have very detailed, precise target labels of how every pixel moved. And it's hard to produce these labels on real data. But it turns out with synthetic data, you can, let's say, sort of animated movies or computer graphics worlds, we can have all the ground truth knowledge that we would want of how things are moving and basically train these kind of motion estimators on synthetic data. And it seems like these correspondence estimators, these motion estimators, generalize remarkably well to real world data. And so what I'm going to talk about are basically using this as a front end for trying to infer geometric structure that's changing over time. All right. And so one thing that's going to be different from the, let's skip this for the time being. The way that, to kind of hint at what I think is some of the innovations in this space, there's been a lot of work on motion estimation, and we have our own homebrewed variant. But let me try to give a couple of intuitions of why I think there's been this kind of cool advances here. So one is this problem of trying to estimate where pixels move from one frame to the next. At some level, what's kind of nice is we can make use of recent architectural innovations and things like transformers. I'm guessing people have heard this term before. But what a transformer is it's something that allows you to, it's predicated on kind of n-squared computation. So the way this relates to motion estimation is that oftentimes classic methods for estimating motion would look at a pixel in one frame and then try to say, okay, do I think it matches well to this pixel in the next frame? And I search over a window. So ultimately, it's kind of an n-squared computation. You look at every pixel in this frame, look at every pixel in that frame, and you try to say how well do they match each other. And it turns out these kinds of, when I compare one element to another element, it fits in beautifully into transformer architectures. And so we can reuse a lot of that machinery for solving this problem. The other thing that I think has been another thing that sort of changed the game is that classically, it's been really difficult to estimating 2D movement of pixels is really difficult when you have occlusion boundaries, because it could be that if I move my hand over a wall, then the previous pixel on the wall that you saw, you can't see it now, so there is no motion. There's no way to tell where that previous pixel moved to. And it turns out you can use things like cost volumes, which look at, by phrasing this task in the right way, you can figure out where you can reliably estimate motion and where you reliably can't. So what I mean by that is, for every pixel you say, how well does it match here? How well does it match here? And if it turns out that it matches equally well to a bunch of candidate locations, then you can say, oh, I don't trust my estimated movement. But if there's one possible match that scores much better than the other matches, you can figure out that you trust this pixel movement. And what this allows you to do is essentially do some sort of uncertainty reasoning. You can tell what pixels you can reliably estimate motion for and what pixels you can't. And now we can use that as a front end for trying to infer geometry. Here's sort of one more, I think, interesting observation that I think has been sort of underemphasized in computer vision. And that is, you can, what I'm showing in the middle slide here is a visualization of optical flow, which is 2D pixel movement. And it turns out that just by, when you match pixels to each other, you can also not just estimate how they shift over from one frame to the next, but you can also ask the question, do I think this pixel gets bigger or not from one frame to the next? And that's an easy thing to do just by looking at image pyramids. So I build a cost volume not over just pixel locations, but I look at different levels of a resized version of an image. And by doing this, what I'm visualizing here on the bottom side is that did this pixel match to a bigger pixel in the next frame or a smaller pixel in the next frame? And if it's bigger, I just visualize it by a white intensity, and if it's matched to a smaller pixel, I visualize it by a black intensity. So this thing in the bottom, it looks like I'm inferring 3D structure, but it's not. All it's looking at is this pixel getting bigger or smaller. So in the biological world, sometimes this is called optical expansion. And in fact, you can show that this reveals something called time to contact. And so what I think is cool about this is you can imagine that if you're a fly, you're moving slowly toward a close by wall, or you're moving quickly toward a far away wall. In both cases, the time to contact is going to be the same, and the expansion is going to be the same. But in both cases, the 3D geometry is really different, and in both cases, the 3D movement is really different. So what I claim is that this kind of thing is easier to estimate, and it actually might be more relevant from a sort of embodied vision perspective. So it turns out that by these motion estimates actually reveal something about how the 3D world is changing. Go for it. Yeah. So firstly, I can imagine I have two images. The simplest way of computing optical flows, for every pixel in one image, I search a window over possible locations in the other, and I just try to match. And so that's kind of what I mean by a cost volume. It's something like height by width by u by v. It's sort of my matching window times every pixel here. And now, if I want to, that will answer the question, do I think this pixel move to the left or above? Now what I'm going to do is I'm going to take my two images. I'm also going to compute resized versions of them. Sometimes this is called an image pyramid. I'm going to shrink them. So now I'm going to ask the same question. Did it move left or right? But did it move left or right? And did it get bigger or smaller? So it's essentially the same thing as a cost volume, but one more dimension. So it's not hard to do, but it is expensive. It's sort of one more axis of search. But when you do it, you get this kind of free estimate about how you think the world is changing. So for example, when the car is moving toward you, you see it bright. When a car is moving away from you, it's actually dark. Even though when you look at it, it feels like it's 3D, it's not. Go for it. Yeah. Yes. Yes. Yeah. I mean, at this point, it's almost like a sampling argument. But there's a maybe I'm not quite understanding the question, but you can imagine, like, there's a continuous world out there, we're sampling it, and if something there is getting bigger, if the camera's moving closer, then the spatial footprint of what we see as it gets impacted on a pixel sensor will get larger. Exactly. Oh, okay, fair enough. Yeah, you're right. Yeah, you're right. Yes, yeah. Yeah, but you're exactly. So your point is that the raw sensor pixel, I mean, like the pixel is the pixel, that's the same, and then I'm going to sort of infuse that resizing as a way of trying to figure out is this getting larger or smaller. So, but I think you all sort of follow this. So essentially the argument is that this is almost a free way within, just by looking at pixel movement, of getting at some sense about how things are changing in 3D. But then this gives you some sense. How do you actually get to full 3D? And this is where I want to lean on this I think, a second revolution in vision and graphics. And that is actually revisiting a very old school way of thinking of vision. And you think about vision as an inverse graphics problem. And that is, you hypothesize possible 3D worlds, or in my case, maybe 4D worlds. You forward render. You say, if this world actually contained a sphere and a rectangular thing, and I looked at it from this camera, what would I see? And then I look at this rendered image, and I compare it to what I actually measure in some frame of a video, and I use that as a signal for optimizing and saying, oh, maybe let me adjust my 3D hypothesis so that it renders something that looks more like the actual image. And so this has been kind of, I guess, created it's been revisited within the context of something called neural radiance fields. And so I think this has been a really cool explosion of machine learning meets 3D graphics. And so the intuition is this, is that we basically hypothesize a volumetric model of the world. And what I mean by that is we actually take a volume of space, cut it up into little cubes, and at every point in the cube, this voxel, we're going to store 4 numbers. We're going to store an occupancy, a number between 0 and 1. That sort of says how solid that space is, and then a color. And then given that soft occupancy, we can compute a rendered image in a very simple way. We throw out array, and we say, what is the probability of seeing a color in a particular place? Well, then it's the probability that there's a 1 there, and there's a probability times that everything in front of it is a 0. So it's 1 minus all the occupancies in front. So by doing this, you can actually compute an expected image that you'll see from a camera viewpoint. And this kind of representation of a world where we have a voxelized representation where things can be soft, this is a very well-known thing in computer graphics, and sometimes it's called volumetric rendering. And it was originally designed for things like transparent or translucent scenes when you have gaseous things where you have partial visibility. So at first blush, you can imagine, why is that a good model of this room that we're in? Because most of this world is empty space and hard surfaces. And it turns out that having this partial translucency or blurry, partially opaque volumes really helps for differentiable optimization, because early on in the optimization, you can hedge your bets and allow things to be blurry. And at the very end, when you keep updating your hypothesis of the 3D structure, eventually it'll crystallize into most of the world is empty and most of the world is hard surfaces. But early on, you get a very blurry interpretation. So I think this has been kind of game-changing. So people have proposed things like differentiable renderers, but one of the key enablers has been actually use volumetric rendering as a technology, because it plays really well with optimization. Okay. All right. And essentially, this is the technique that I'm going to use. So we're going to hypothesize this, this volume on the left-hand side. I'm going to hypothesize a bunch of cameras about how I'm looking at it. And importantly, because the world is changing, I'm going to hypothesize that some way in which this volume is deforming over time. Given all those things, I just press my render button, my graphics rendering button, and I generate a bunch of images. And now I can look at the difference between the generated images and the actual frames of a video, use that as an error signal, and then try to update all of my hypotheses about my blurry volumes, my cameras, and my deformation, so that they render things that look like the actual images more. So this is an optimization. And then let's say the key difference between, I guess, the kinds of things we've been looking at, let's say, than what is the norm, is that in addition to rendering images, we also render motion. So because we have some estimate of how we think the world is changing in 3D, we now say this is how we think it would translate to pixel movement. And now we look at the rendered optical flow, and we compare it to the measured optical flow, and that's an added signal that we use to now refine our guesses about what's happening in the world. Go for it. So importantly, we're going to use some off-the-shelf network that, just given pairs of frames, tries to predict correspondence by looking at cost volumes. And that network was typically trained on synthetic data, because it's so painful to annotate and supervise training for this kind of prediction problem. Cool, go for it. I'm not following. Which pixels are you referring to?
So those color changing.
The color changing pixels. I sort of like here?
No, yeah, the right hand side.
The right, these things. It's a visualization of flow. That's all. Exactly. Yeah. It's just you can't, unfortunately, yeah, it's too small, but it's just little arrows. And I'm doing color, so blue means it's moving left, green moves moving right. I don't quite follow the question. So this is just, from the perspective here, you run some off-the-shelf optical flow network. So given a video sequence, you see pixel intensities and you see 2D motion vectors. Hopefully they're accurate. They're going to be noisy. And I think there's been this innovation of you can actually, if you use a contemporary optical flow network, if you use it in the right way, you can, what I would call sort of, I think you can use it reliably for semi-dense flow. So for a lot of pixels, it knows where it's going. And then for certain pixels where it doesn't know, it can at least tell you, I don't know where the motion is. But we can supervise just on those pixels that we know. And the real sort of insight here, I think, is that we all know that in some level, one of the reasons that we're having this sort of AI renaissance is because of innovations in compute. Like GPUs is what enables a lot of this machine learning and AI technology. And of course, GPU stands for graphics processing unit. So all of that research and innovation was really buttressed by the computer gaming industry. But now NVIDIA actually makes GPUs that are specially purposed for deep learning. And now what's kind of funny is that we can use all of the machinery of parallel processing and all of these remarkable software toolboxes like PyTorch and Atom optimizers. We can use all of that differentiable optimization to solve an inverse graphics problem. And in fact, that's what we use here. We're using all these software libraries that are originally designed for neural network optimization. They work really well for optimizing this thing. OK, go for it. Yes. Exactly. So yeah, so a traditional NeRFs assume that you know the cameras. But I want to start with this setting. If I'm just given videos and I don't know anything, all I have is the pixel evidence. So ultimately, if I have these three things, if I have shape, motion, and cameras, and I press my forward render, it generates images and it generates 2D flow. And I just use the difference between that and what I actually measure. Yeah. But you're right. Traditional NeRFs are an easier form of this. And so we have to solve a harder problem here. Yeah. Yeah. So there's different innovations there. I like thinking of it as a lookup table. It literally is a 3D thing where for every XYZ point in the world, I have a color and 3 numbers and then an occupancy sigma between 0 and 1. But there's sort of different variations of that now. So maybe I'll show off a couple things that I think are super important. So one thing that you hinted at was that traditional, it's really important to initialize this optimization nicely. And so some things that we've been working on as well is because most work assumes you have high quality cameras, it turns out you can actually learn feed-forward models of given multiple frames of a scene that will spit out guesses of what the cameras look like. And this is actually a recent piece of work that will be published in iClair, which is kind of a fun visualization of using a different parameterization of cameras, where instead of trying to predict some extrinsic rotation and translation, it turns out from a neural network perspective, it's really nice if you over-parameterize cameras as a collection of rays. This is actually a well-known, or not I should say well-known, but sort of an old representation of cameras known as Raxels, introduced by Sri Nair, that was useful for modeling cameras that are sort of special, that have, let's say, different kinds of distortion. And it turns out that just by trying to train a network that predicts for every pixel a ray, when all those rays agree and intersect at a pinhole, that actually is a well-defined camera. So this is a very redundant, over-parameterized way to represent a camera, but it works really well for neural network prediction tasks. So we call this cameras as rays. Happy to talk more about this, but this gives you a way to initialize this model in a nice fashion. And then, of course, I didn't really talk about how we model deformations. And the insight really here is we just do what graphics people do. There's sometimes something called a skin and bones model. It's a visualization provided here where we assume that there's, let's say, 20 canonical bones or control points, and they're visualized in these colored circles. Each one of these gets to rotate and translate over time. So we'll parameterize that with an SE3 transformation. And now we assume any point in space from this canonical volume also deforms in a linear combination of these 20 things. So sometimes this is called a linear blend skinning model. And so from the perspective of this talk, we just think about this In graphics, there's kind of representations that deal with answer this question of how things deform over time, and we can just use them to deform our canonical world. Okay. And now, importantly, this thing that I'm talking about now can be run on different videos of deforming things, and it will try to infer some 3D structure that's dynamic and changing that renders well. So importantly, the results I'm showing here had no 3D database of cars or camels or cows. It's just trying to find some deformation of some canonical model that matches all the pixel intensities and matches all the flows. So importantly, yeah, this is maybe there was no. In some ways, I guess I want to stress here is that this is not really the big data story that we're used to seeing from AI. I think of this as almost a small data story. This is just given one video sequence that maybe has a few hundred or 1,000 frames, fitting an explanation of some dynamic world that agrees with that visual evidence. Go for it. Got it. So right now what we're doing is we have some kind of motion segmentation algorithm that's also running in the back. So we try to find, given all these movements of pixels, we try to group them into foreground and background. Okay, go for it. Yeah. So that's a great it's a great question. So I guess one way to think about this is that I haven't directly connected this back to self-driving. I think about this as almost as a way of learning 3D, 4D structure that's very expensive. And this is done on a per scene basis. But then what I want to do is, in order to actually run it in an embodied setting, I think I want to distill this into a feed-forward model that takes as input frames or a sequence of frames and spits out this stuff. Okay, I'm just going to keep going just to kind of move on to some of these results before I take some more questions. Okay, so here's some sort of fun examples of what you can do when you fit this. So one question I usually get is, isn't this fitting problem like under constrained? Like, aren't there multiple interpretations of how the world could change that would generate the same evidence? And that's true. So we've kind of done a bunch of work on trying to find more constraints. And so one of them is if you have more different kinds of sensors. So everyone in their back pocket has a multi-sensor camera rig. This thing has 3 cameras on it, including a lidar sensor. And it turns out that from your cameras you can get both RGB plus depth. And now, just as I talked about before, we're trying to fit models that, when we render them forward, generate images that look like the real image. I can also try to generate 4D models that, when I render depth, it looks like the measured depth. It's just another signal that I can use for backpropping. And if you do that, we can build even more richer models of the background plus the moving dynamic objects. And some fun things you can do that is very NeRF-like is we can render this from novel views. And so this is an example of rendering a sequence from a virtual camera put on the ceiling. But because we're actually reconstructing the dynamic things that are moving, we can do kind of more fun stuff. We can put a virtual camera in front of the cat's face and then render the world from the cat's perspective. And we can even put a camera like right behind the cat, sort of visualized in blue here. And this is what a little sort of selfie drone would see if it was following the cat. And because it's a dynamic reconstruction, I can press play and let this thing move. So what's kind of fun is this is the view of what the cat saw as it was moving around. And all of this is generated just from this one video clip that is about, let's say, 15 seconds in length. Here's some sort of more examples of, in this case, this is our local office of someone playing with their dog. So these are sort of fun reconstructions. You can see in some cases you see white pixels on the right-hand side. And those correspond to pixels that we never saw in the input video. So you can imagine, either in that case, maybe you want the model to take its best guess. Right now we've set it up where it just says, I don't know what that part of the wall looks like. But this is sort of one place where presumably a big data perspective would help. Although I haven't quite seen that corner of the wall, I kind of know what buildings generally look like, and so I can probably make a good guess of what that pixel would be. So we certainly haven't done that yet. I like this kind of view. On the bottom right-hand side, it's kind of remarkable how much you see of the other room just from that one video sequence. And this, to me, almost looks like a third-person kind of game when you're controlling a virtual avatar. And so there's been incredible innovation in this space, not by us, but by quite a variety of folks. And so now it turns out you can make these things, the optimizations. When we first did this work, sometimes it took like half a day to optimize on a video. Now, by using kind of optimized graphics primitives, something called Gaussian splatting, you can do this in an interactive fashion. It's an example on the left-hand side where we're re-rendering the world from the point of view of a rotating ball. So that's kind of cool. You can see it spin around. On the right-hand side is an example of putting virtual objects into a scene. I'll just sort of show some examples there. Something else that we've been pushing on, maybe a bit more from the self-driving perspective, is really pushing this for scale. So on the left-hand side is an example of a student basically took a drone out and he flew this over about 1 kilometer square area. This is a region in Pittsburgh where we're going to build our new robotics building. So there's lots of construction going on. But once you built this model up, you can then fly around and get sort of virtual reconstructions. And because this took, let's say, a couple hours to collect the data, the sun changed positions and actually changed the way the pixels looked. And it turns out that there's ways of capturing those appearance changes in these models as well. Maybe I'll just give a little bit of hint. Oh, sorry, here. We've pushed the scale all the way to almost citywide reconstruction. So back when I was working at the self-driving company, actually assembled logs from a year's worth of data of cars moving around the streets of Pittsburgh, and I actually tried to build a dynamic reconstruction where now you have to deal with the fact that seasons change, and sometimes you see green leaves and sometimes you see brown leaves. But it turns out you can use the same kind of appearance modeling techniques to capture that. And maybe I'll just give a little sense of, in order to push these things for scale, the insight to really make this work is, I think, the same story of lean on more of good old graphics intuition. So way back in the early 90s, people built pretty impressive graphical simulations of buildings, of interactive walkthroughs that could be done at real time before we had any of these fancy NVIDIA GPUs. And the way that they really made these things work is making use of visibility reasoning and a multi-scale reasoning. So even though there's a big world out there, you only see a small part of it at any one point in time. And by quickly figuring out what part of the world that you see, you can make this work really well. And it turns out we can use those same visibility reasonings to decompose these volumetric reconstructions of an entire city where if I look at all the images from one place, I don't really have to think about pixels from another corner of the city to help do the reconstruction here by applying these same kinds of visibility techniques. Let's see, so the interest of time. Something else that I think we've been thinking about more is, in addition to making use of differentiable volumetric models, differentiable renders that are enabled by volumetric modeling, can we apply the same intuition of coming up with a differentiable way of describing movement? And so this is, I think, also a really kind of just a space that's just starting out, which is you can take physical simulators and figure out a way to describe movement of a world that's also differentiable and amenable to gradient-based optimization. And the reason why normally physical simulation is really hard to do gradient optimization on is, think about me modeling my foot, and if I'm a millimeter off the ground, then there's zero force that the ground is exerting on me. But if I move my foot infinitesimally small, then there's a huge force the ground is exerting on me. And this kind of thing makes it really typically difficult to do gradient optimization because it's not Lipschitz. I make a small input, results in a large output change. But I think if the same intuition for volumetric rendering applies, if I instead model the world as squishy, if I said the whole world, if this was all a spring mass system, like a big soft bed, and then as I press down, then the force gradually increases, then that actually is amenable to gradient-based descent. So people have started applying these same kinds of, you sort of model the world intentionally in an inaccurate way, just so that it's easier to optimize. I think you can now fit models that try to estimate masses and forces that best describe how things are changing over time. And that's a visualization on the right-hand side. I'll talk about the details of the math. I'll skip for now. I know we're sort of close to the end now, but I wanted to take a quick pause and sort of say the story so far was really the thing that I walked away with after sort of time in the self-driving world was that it's somehow really a geometric problem. It's a good old vision problem that seems like something we should have solved, but I don't think we really have. And it's how do we really build stable interpretations of things that are changing and dynamic over time. And I think one of the big innovations we have is basically reunifying our representations with graphics models, with forward models that are designed to capture how the 3D world looks and how it's changing over time. And I think the enabling technology really here has been differentiable forward models. And a lot of that, maybe the special sauce that we've been pushing is really driving that all by motion estimation. If your focus is really on dynamic models that are changing over time. Okay. So I know that we're sort of out of time. I only have a few minutes here, but I wanted to, let's say, switch gears a little bit and just talk about another aspect of perception that we're excited about, and I think there's also lots of work going on here that I'd love to talk to folks about, and that is like multimodal perception. So I already gave the hint that cameras and depth, unifying them together really helps. I showed this example of if you get a video here that has multiple sensors, it really helps this fitting process. So we've also done work. I guess maybe the most conspicuous example of sort of multimodal reasoning in today's world is vision and language. So I thought I'd sort of hint at some interesting, what I think are interesting perspectives, and I'd love to get more feedback on this. So one starting point that for me was that if we think about perception for the self-driving case, what was kind of striking to me is that a lot of times we focus on analyzing detection performance on well-known categories such as cars or people. But it's fairly easy to show that if you're trying to look at performance of things like wheelchairs, you don't see them a lot in these data sets. And so it becomes really hard to evaluate performance. And in fact, there's a lot of the status quo might even be just to ignore, don't even evaluate wheelchairs or strollers because we don't have enough of these things in our data sets. So it must be the case that that's the wrong way to frame the problem. You don't want to build a safety critical system that just ignores things that are rare. So there's lots of analysis that we've been trying to do to kind of alert this problem. But one of the, I think, really attractive solutions is really this revolution in big data via foundation models. So right now, I can go into DALL-E 3 and type in stroller with 3 wheels in the winter pushed by man. I can get pictures out that are kind of reasonable. And I would claim that this doesn't exist in any real autonomous vehicle data set because for various reasons, most strollers are 4 wheels instead of 3. People don't usually put strollers in the winter. And unfortunately, they tend to be more females rather than males. But on all these cases, this is a very rare example that I think doesn't exist in a current data set. And so, but it's amazing that we can kind of generate images that look like this. So I think that bringing to bear these large-scale massive models is super important. And maybe I'll try to advertise, I'll sort of skip this for the moment, something that we've been thinking about that relates to, I think, a lot of things that folks here have been looking at, which is how do we think about open world processing in the context of foundation models? And so a problem that at least I've looked at in the past is something like zero-shot recognition or few-shot recognition, where you train on the typical formulation of this is, let's say you train never having seen a truck before, and then you ask the question, how well does your model do at recognizing trucks? And then the thing that I'm kind of struggling, that we're struggling with, is what is the right way to phrase this question in the context of foundation models? Because foundation model says, is essentially it's a model that's been trained on massive data that you might not even know what it's been trained on. It might be proprietary. And right now, the way that this problem is formulated, it seems like they can't even enter the conversation because we formulate it in such a way, we're like, no, no, you have to make sure you don't train on trucks. And then you can join the conversation and we can see how well you do on trucks. And so my guess is that way of framing it, we need to figure out a way to allow foundation models to at least be evaluated so we can see how well they do, because their performance is sort of undeniable. So maybe we need to, let's say, so here's one version of it that we've been thinking about that I think is actually intriguing, and that is framing it in such a way that is still few-shot but exploits the multimodality of this problem. And what I mean by this is, I remember in my time at the startup, one of the most painful parts about annotating data, and we went through this task, if we want to build a large-scale data set and annotate all the cars and construction vehicles and wheelchairs that we find. And one of the most painful parts, one of the most difficult parts, was actually defining what we meant by a wheelchair, or defining what we meant by a bicycle. Like our certain, so a question we would get is, okay, annotate all the construction vehicles in the scene, and then annotators would say, well, is a crane a construction vehicle? What happens if the crane is physically mounted on the ground? Or what happens if I see a reflection of a person? Should I count that as a person or not? So what happened is we do all this sort of feedback between the annotators and the curators of a data set, where we actually refine what we mean by the concept that we're trying to annotate. And oftentimes that gets materialized into a set of instructions. And so what I'm showing here are actual instructions from various well-known data sets, such as new scenes, where this is the instruction that describes what it means to be a bicycle rack. And the instruction itself is naturally multimodal. You have a bit of text. You have a few examples. In fact, what actually is really fascinating, the examples that are chosen are very deliberate. Sometimes you show a very typical example. Sometimes you show corner cases. Sometimes you show what a bicycle rack is not, with a red box. And that helps explain to the annotator what we mean when we say bicycle rack. So one thought is that actually this is what we should think of as few-shot learning in today's world. It's multimodal. You present few examples. You can bring to bear any prior knowledge that you've seen, but we're going to see how well we can do at almost learning from the same set of instructions we would give to each other when we define a class or concept. So we're putting together a challenge on this in an upcoming CVPR workshop, so I'd love to see if there's interest or get feedback on how to phrase this better. So maybe I'll sort of end there. Yeah, so we sort of talked about the first two things, which is really motivated by doing better perception for I think sort of embodied navigation. And then I think there's this incredible opportunity. The first two things really weren't about big data. It's really more about graphics, trying to fit a model of a 4D world using our knowledge of how the structure should behave. But then I think sort of a game-changing capability that we can't deny is, what can we do with all this massively learned knowledge? But I think that does require rethinking the way that we formulate some of these open world problems. So with that, I'll conclude and take any more questions. Yes.
Sorry, please go to the mic possible. Thank you.
In EC here at BU. So you mentioned that motion estimation is very important in all these dynamic worlds. Of course,
Yeah.
it is. I worked in motion estimation for 40 years.
I see.
And what's interesting is that today motion estimation by let's FlowNet 3 or something like that, it's good, it's better, it's not blowing out of the water Horn and Shanks and Lucas Canadas of the late 70s and early 80s, and gazillion improvements ever since. it is unlike in deep learning, segmentation, recognition, classification. All model-based methods are just not comparable into deep learning. Motion estimation is in the ballpark. So is it that this is the physical model that in motion is reasonable and is difficult to emulate in deep learning, or what are your thoughts on that?
Yeah. So I guess there's, I guess one version is that I think that not enough people are working on motion estimation. So I guess one narrative I try to advocate for is that I think there has been innovation in there. The place where I still feel like maybe there's stuff to figure out that might require more model-based interpretations is how do you do long-range motion estimation? So like the most sort of bare bones version of this is two sensor measurements, 2 frames, try to estimate how things are moving. But it could just be as you get more and more sensor measurements over multiple frames, that's a richer input to try to figure this out. But of course now you have to deal with the long-range problem. That there it's even more likely that things become occluded or leave the view. And at least the angle that we've taken there is that if you're trying to answer those questions, it's best to do by leaning on 3D as a first-class citizen. So in some sense, the way I think about these 3D models that I'm showing you, in some ways they're emergent by trying to explain all these little long-range motion estimation is via 3D. And you're right that final thing that we show, it doesn't really look like a deep network. It really looks like a differentiable volumetric renderer. But in that sense, what we're using on the deep network almost as a front end to get local but noisy motion estimates. And we're using this, let's say, much more classic geometric model as a back end to put everything together.
Thank you.
Yeah. Go for it. Yeah. Yeah. Yeah, great question. So so for example, even the motion estimators that we're using were trained on flying things 3D. So in some sense, maybe that's a disappointing result that we're still training on the same synthetic stuff like from back a few years ago. I think one reason is that maybe my impression is that the domain gap is not as big of a deal as opposed to if you're actually trying to build like object detectors from synthetic data, then you're actually looking at the raw pixel values. You have to make sure that that's really rendered in a photorealistic way. And instead here, what we're really trying to do is estimate, I think of this as we're really trying to build a correspondence machine. We're trying to figure out what pixel here mapped to what pixel there. And it could be that, or rather, it seems like to answer that question, maybe we don't have to generate really photorealistic pixels. We can still do kind of silly things like construct scenes with chairs flying around and learn how to find correspondence there, and that does seem to translate okay. It's decent, but they can definitely be improved. So like, I still think one of the big ways to improve them is really, I think there's this growing body of work on like long-range motion estimation. Sometimes like particle models. And a lot of them, in some ways, almost look a bit like this. They're almost, at least my own bias view is that if you really want to do long range, it has to be 3D. But so I will still say like long range motion estimation is still difficult. I'll go for you next. Yes. definitely. Yeah, it's perhaps the trickiest part of initialization is camera pose. So that's been sort of one of our focuses. I showed this kind of perhaps mystical thing that said, okay, instead of trying to predict initial camera pose, we can almost predict rays for every pixel, and that's kind of this distributed representation of a camera that turns out to, at least in our experiments, to be a more effective way of doing it. But I think camera pose is one of these big things. And someone else asked this question, rightly so, that all these results on NERF, they're beautiful, but I think they all require like very high precise camera pose. And so it is probably the big linchpin of all of this is like getting good estimates of where we think cameras are. And in some sense, when you have a moving object, that what you really need to do is estimate the camera relative to the object. So even if you have perfect cameras, once you have moving objects, it's as if you have to still solve the pose problem. You have to tell, am I looking at a front view of a car or a side view of a car? If the car is moving and rotating, even if I know my camera, I still need to, that's still a hard problem to answer. Yeah. I'll go for it. Yeah. Yeah, so the place that I see this is kind of what I hinted at with this this notion. So like right now, if I go in, okay, let me give one version of this. I'll do it through the lens of self-driving. So there's different self-driving data sets. So Waymo has released one, New Scenes has released one, and it turns out their definition of bicycles is different. In Waymo, bicycles should include the person. In New Scenes, it should not. There's other slight definitions as well. So because of that, if I just take a foundational model and run it on one of these data sets, and I say, find me bicycles, it's going to screw up because it doesn't quite know what I mean when I say bike. It doesn't really know what a Waymo bicycle is. Yes, yeah, but it can even be more than text ambiguities. For example, I really do think this is directly analogous to instructions. So even when we label bicycles, what happens if you only see a corner of a wheel, like 10% of a bicycle? Should you label that as a bicycle or not? And that's almost a definition of what it means to be a Waymo bicycle. We have certain amounts of occlusion. So that's a little bit more of a spatial definition as opposed to a textual one. Yeah, well, it's because I think it's the nature of a model that's been trained at scale on noisy data. Like the way that someone on the internet talks about bicycles, I don't know why that has to be the way I talk about it in Waymo, because that's just, that's the messy wild, wild west of the internet. And so I think I guess what I'm claiming is for any target application, we usually have some sort of, I don't know, target concept in mind. And I actually think this is directly analogous to exactly the conversation we have with annotators. We saw this even in Coco. So one of the things we did in these early data sets is we asked people to annotate hot dogs in images. And it turned out sometimes, especially depending on culturally where you were, you might not know what a hot dog is. So is a hot dog a type of sandwich or not? And people will disagree with that. And I don't know if a foundation model should know the answer to that. It's almost like a conversation that we have when we sort of ask people to annotate. We say, no, this is what we mean, and we give you all this sort of stuff so that you know what we mean. Exactly. So I think that's not all of the problem, but to me, that's one of the big how we should think about few shot. You know, we have a few examples, they're multimodal, and it's to a person, this is what we mean when we see a Waymo bicycle. Okay, go for it.
So I have a question to make sure I understand correctly one of your demos. So the one with the cat and the dog, the second video,
Yes.
where you have a video, you are learning three-dimensional dynamical model from which you are constructing other viewpoints of the scene.
Yes.
Correct? So in order to do that, you are processing the whole video,
Yes.
and only then you can do because you're learning structure and texture mapping from different dynamic motion of the cat and the dog.
Exactly.
But you cannot do it in real time
Exactly.
because you don't know.
Yeah. 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 So all of that was like an offline optimization.
I understood it, but I want to make sure.
Yeah. No worries at all. Okay, go for it next. Sure. Sure. Yeah. Yeah, it's a bit like what would happen if even there's spatial locations that I don't know about, and those are the white pixels. And depending upon whether the back end there's some neural parameterization or whether it's really more of like an explicit voxel, like if it's more of an explicit representation, you'll just see nothing. If you have an MLP, it will do something. But at that point, I don't really trust it, I guess. But the way I would think about this is that, like, with all kind of data-driven efforts, I actually feel like we don't really have a lot of space-time varying data. Like, it's really hard to do data-driven models of behavior because we don't really have large-scale data sets. And so the hope is if we can actually do this and kind of objectify videos that we just download from YouTube and actually understand how things do move with relation to each other, then maybe we can actually build stuff. And then there, we have a better chance of sort of this data-driven extrapolation. But this is really taking a much more of a bare bones of just fit to the pixels you have in front of you. And if the pixels aren't there, like, throw your hands up and say, we don't know what's happening. Go for it. Yeah,